right, so for example 1, we have 3 different graphs, and part of D1 is that you're able to, and if we go back to our standard here at the beginning, you have to be able to define, give a thorough definition for a derivative, and you have to be able to demonstrate whether you know a function is increasing or decreasing using a table and a graph. So the one I did here in this spot, we're looking at the door closing around the time equals 3. That was using a table to see if you know if it's increasing or decreasing. And then for example 1, we have 3 different graphs, and we're going to look at each one of these graphs to determine if the function is increasing or decreasing, and is it fast or slow. So a couple things here. Fast or slow, that refers to rate of change, which when we were looking at the table, example yesterday with the door, the rate of change had to do with the slope of the graph. Now we can't physically zoom in on these 2 spots that we're indicating here, but we can imagine, we've talked about if you zoom in close enough around that point of A, the closer you get, the more and more that curve on your screen would look like a line. And so we talk about the slope of the graph, even though obviously this is not a line, so it doesn't have an actual slope like a line would have a slope. But around that point we can identify a slope. So we do that by drawing in a tangent line and then estimating the slope from there. So at A, a tangent line, can someone remind me what tangent line is we talked about yesterday? It touches it at that one point that you're looking at. So, and then it just keeps going. So like if you're looking at a circle, tangent line to a circle just touches it in one spot and keeps going. A secant line goes through it. Okay, touches it in twice. But we're just talking about tangent lines, so it just touches in that one. So as best you can, you draw on a tangent line that follows the curvature of the graph. Meaning, you're sketching a line there that the best you can draw in follows the slope of the graph. And then we're going to do the same thing over here. At that next point, drawing in a line follows the slope of the graph. Now, from these tangent lines, there's 2 questions we have to answer here. For point A, we have to talk about whether the function is increasing, decreasing, or neither at that point. And then we have to describe if it's increasing or decreasing, is it fast or slow. So I guess the first thing we should identify here, is this function increasing or decreasing or neither at point A? It's increasing. Give me one reason how you know. The graph itself is going up from left to right. And what is the tangent line doing? It's going up. Okay? So our graph here, f of x, is increasing. And then we're going to identify if it's increasing quickly or slowly. At A, isn't it kind of slow? Because is this line, if you look at the tangent line and we think about what that slope would be, that slope is going to be a pretty shallow slope. It's not increasing very quickly because the line itself isn't very steep. So at A there, we're going to say it's increasing slowly. And we identify the slowly part by looking at the slope of that tangent line. So at B, Kenny, is f of x increasing or decreasing? Increasing still. Increasing still because your slope is positive. Your line is positive, increasing. And then what about quickly or slowly? It's going quickly because your line is much more steep. Good. So f of x is increasing quickly. Okay, we're going to do the same thing for A and B here. Best you can, I want you to draw in or sketch in a tangent line. For both A and B there. Okay. So your 2 tangent lines at both those spots should look kind of like that. All right, so Brendan, describe to me what's happening at A. It's decreasing. Look up the steepness of your line. Is your line fairly steep? Pretty quickly. Okay, so your f of x is decreasing quickly. Josh, describe B to me, please.
It's decreasing slowly.
Good. So f of x is decreasing slowly. All right, and then we have 4 points here. I'm going to zoom in on this one a little bit. All right, so when you sketch in a tangent line here, it's going to be very steep. And then B. And then C. I'm going to draw a little mini one. And then D. Okay, so you're drawing your 4 tangent lines. Then we're going to describe each one of these. All right. Bree, can you describe what's happening at A for me? Okay, so f of x is increasing quickly. Good. What's happening at B, Evan?
At B, it's
Increasing more slowly. Good. All right. What's happening at C, Kenny?
decreasing slowly.
Decreasing slowly. Good. And last one, Will?
D is increasing quickly.
Good. Can anybody identify for me what situation we haven't seen yet? Oops. That's increasing.
Equal neutral one.
An equal or neutral one. Good. So f of x is decreasing quickly. Does anybody know where a function will be neither increasing nor decreasing? At a maximum or minimum. When you have a hill or a valley, so a hill or valley, the very peak, it would be a horizontal tangent line. And what's the slope of a horizontal tangent line? 0. So you have no change. It's not increasing or decreasing. It's just neither. Just there. All right, so that's a situation where you would have either increasing or decreasing at a maximum or a minimum. That fact right there is going to be super, super important with derivatives as we get through some of the standards, okay? Where you're going to have max or min.
Just say neutral.
You would say f of x is neither increasing nor decreasing. It's unchanged, yeah. All right, and it's just at that, as soon as you're not at the peak anymore, are you going to be decreasing or increasing? So it's just that instant where you have the peak. Okay, for example 2, we'll talk about this. And then for right now, you can exit example 3, because that one I'm actually going to have you do with a partner today. So, for example 2, average versus instantaneous examples. Okay, so average rates of change. We'll label this. Versus instantaneous. I have a sneaky feeling that when we're doing notes as a whole class, because it's so quiet in here right now, that the culprits, I'm pretending class today, the ones that distract us. All right, so average rates of change, instantaneous rates examples. So a very common one, if you're talking rates of change, is speed. Okay, so if you're talking about speed of a car, what would make it an average rate of change?
Gradually increasing. Like coming out of a stop sign, gradually increasing.
If it's between 2 points.
Yeah, steadily increasing, coming at a stop sign, but what you're talking about is some sort of passing of time, right? Acceleration or deceleration, but you're looking to make it an average rate of change. You're looking at a speed of a car over a period of time. Okay, so in this example, say speed of car over a period of time. This is how all speeds are given to you. So like when you talk about how fast you're going in a vehicle, you're talking about like 45 miles per hour. Because that's over a period of time. You're talking about over an hour. Okay? So if that's your average rate of change, what would be an instantaneous rate when you're talking about speed?
Suddenly you're going 0, and then split second later you're going 80.
Not even a split second.
It's instantly.
It's instantly. So we don't even need a change. We would just say not the speed of a car over a period of time, but you'd say the speed of the car at a particular time. Okay? So speed of car, or speed at an exact instant of 2 minutes. So let's say, we should probably label these. So average rate, and this is instantaneous. Okay? Does that make sense?
Yeah.
Now if we're talking about the same vehicle, could we say that probably at 2 minutes, at that instant, he or she is going close to 45 miles per hour?
Yeah.
If that's your average? Yeah, but can we say for sure that that's exactly 45 at 2 minutes?
No.
No. Because when you do an average rate of change, you're looking at all the little dips and increases over a period of time to get the average. Well, we could say the instant that 2 minutes has occurred. Yeah. All right, so the other one that we have talked about in terms of average rates of change or instantaneous rates of change, we've looked at degrees per a period of time. So in that case, something else that uses degrees would be the average position of the sun in the sky, because we would reference it in terms of like how many degrees have passed in terms of the sun moving. So average position of sun in the sky, so how many degrees per hour it's moved across the sky from your reference point. Okay. And then the instantaneous, yeah, the exact position of the sun at a particular time. So let's say at 2 o'clock p.m. or something. Okay, so you need to get in your mind, when you're looking at average rates of change, you're looking at a period of time passing. An instantaneous rate of change is one specific time value, not a range. Okay? So those, you would have to come up with your own. Those are 2 examples to start with at least, and we'll have practice where you're working with people to try to come up with other examples so you have something to pull off of for the test. But that kind of completes D1. And if we flip to D2, we're going to go right into this because it'll piggyback off the examples that we've already done. For this is estimating values of the derivative. Remember, the derivative is the rate of change. What kind of rate of change is it?
It's an increase or decrease in change.
It's a specific, we just got done talking about 2 different types of rates of change. The derivative is one of them. It's not average and instantaneous. It's only instantaneous. Okay? So the definition of a derivative, if we look back here yesterday what we wrote down, derivative of f of x at a particular value is the instantaneous rate of change at that value. Okay, so derivative is the instantaneous rate of change.
Sorry, my screen went blue.
Alright. So, that being said, we are going to have to estimate, because I haven't taught you all the rules yet to find the instantaneous rate of change, but we can get really, really close to an estimate, kind of like what we did yesterday with the table. We'll do similar things today. You're going to learn 3 different ways information is given to you when you're trying to estimate the value or the instantaneous rate of change of something. We are going to do examples for each set of information and then summarize how to set it up. Okay, so when you're given a graph, We've done an example like this already. But when you're estimating the derivative given a graph, you want to first do what? What did we do with this example? What was the first thing we did?
Made the tangent lines.
Made the tangent line. Okay? So that's the first thing you're going to do when you're given a graph is you're going to draw a tangent line to the point in question graph. Meaning, whatever, and maybe I should say, or identify, the point I'm talking about is the x value. So if they're saying estimate the derivative at x equals 6, then you're writing, or you're drawing in a tangent line at x equals 6 on the graph. Okay? And then when you're given a graph and you're supposed to estimate the derivative, derivative is the instantaneous rate of change, and the rate of change we can look at as also the slope of the graph. So when you're looking at a graph, we can estimate the slope, which is another way to say rate of change, by counting boxes to find rise over run. Okay? It's difficult to estimate slope if you don't have boxes in the graph. So a lot of the times I give you ones to estimate slope. I will give you one that has grids. Okay? So for example 1, this follows this type of information that would be given to you. You're given a graph that shows the height in feet of a soccer ball above the ground as a function of time since it was kicked into the air. Okay, so soccer ball is kicked in the air, the height changes, increases, and then slowly decreases until it hits the ground again. For A, we're supposed to estimate the instantaneous rate of change at time t equals 5. So, Kenny, what do I do?
First you draw your tangent line.
At what value?
At the 5 second.
Yeah, at 5. So you go to where the question, or the time in question is, at t equals 5. We're going to go to where t is 5 on our graph, which they've actually already identified with a little point here. And you're going to draw your tangent line. Okay. So we can see that it's decreasing. So let's talk about this a little bit. It's decreasing, which means what's happening with the ball?
Going down.
It's going down because the height is decreasing. Okay. And the slope, is it steep or shallow? Pretty steep. So is it going quickly? Yeah, so it's decreasing quickly, which makes sense if it's falling towards the ground. The gravity is going to help it pick up speed. To estimate it, you're going to actually count boxes here now to find rise over run. Now, when you're drawing your tangent line, the key here is we're looking for these 2 grid points that it passes through. So they identify one grid point for you. I would use that point right there. And then we find another point where my tangent line passes through a grid point. So let's say passes there. Yeah. Maybe there. Now, depending on how well you draw your tangent line, everybody might be a little bit off. So when you show, it's going to be close. But when you show your work, you need to draw on your tangent line. It can't be all wonky. You need to make sure it's straight, which usually students will use the arrow feature or something if you're doing it on the iPad, or if you're doing it on paper, then you just use the edge of a paper or something to make it a straight line. And then you find 2 grid points, and then we're going to do rise over run. So from this grid point to this grid point, we have to go up 2 and over 2. Now watch your units. Because are your X tick marks worth the same as your Y tick marks? No. So your rise over your run. Your rise is you're going up how many actual values? You're going up 2 units, but it's worth 20, right? So we're going to go up 20. And then what direction?
Right 2.
To the left. To the left 2 units, right? Okay. So left 2. Okay, so up 20, left 2. Can I reduce that? Up 10 over 1. but to the left 2 identifies it as a negative value, right? So we should have negative 10 as our final slope here. Should be negative because you're decreasing. And we need some units here because this is a rate of change. So what is this? What over what? Feet per second. Yeah. Usually if you're given a graph, if you look at your labels for your axes, it will give you units. So feet over seconds, rise over run. So now we're going to give the mathematical name of this instantaneous rate. What is the mathematical name of an instantaneous rate change? Derivative. Good. So this is a derivative. Mathematical name for an instantaneous rate of change. And state why the rate is negative. We already talked about that. Why is the rate negative? It's decreasing. What's happening with the actual ball? The ball is going down. So the ball is falling back toward the ground. So h of t is decreasing. So when I ask you to state why the rate is negative, or sometimes you have to talk a little bit about the problem, if it's talking about an actual situation, which a lot of these will be, you have to actually state what's happening with the object or the situation at hand. You can't just say the function is decreasing or increasing. You have to tell me what's actually going on in real life. Okay. Any questions on that one? All right. So then the next type of example that you will see is when you are given equation. Okay? Which we have not done one like this yet. Oh, kidding, we have. That was our door example because I gave you an equation for that one. All right, so for number 1 here, we haven't done this part yet when you're given an equation. I'm going to show you a little shortcut because remember with our example yesterday how I had you plug the equation in, you evaluated your time values and then your d values, and then you had to do all this work at the end? Remember that? Yeah. Okay, I'm going to help you shortcut this process, right? So on step 1 here, we're going to make our average rates equation. So we're going to set up your average rates equation. And this is how I'm going to label it. R of x equals, now rates of change are change in y over change in x. So when we're given an equation, we're given an f of x, which is the same thing as saying y. So we're going to do the change in f of x. That means you're changing your y values, the same thing as rise, over the change in your x values, which is the same thing as run. So slope, basically what we're setting up here. And we're going to use the x value in the question. Now, if you don't have a calculator, it would be good for you to have one for this particular problem. So I grab one from a table around you because there's lots scattered around. Okay, once you set up your average rates equation, we're going to put your new average rates equation into your calculator. And you're going to look at the table. So basically what we're doing is we're shortcutting the process we did before. I'm not making you find y values of the equation. I'm making you come up with a new equation, actually put your average rates equation that we did by hand. That's the actual function we're putting in. And then we're just testing the same x values that we would have before. But then the answers mean average rates of change, not just single y values. Okay, so we're going to test, look at table, and then we're going to test values, say x values close to c. C being the x value that we're looking at. And we're going to use this to estimate our instantaneous rate of change. say the graph, but we're not going to actually use the graph here to estimate because I don't give you grid marks here. So we're not going to be able to really easily count a slope or figure out a slope of the graph. And when you're given an equation, this is much more precise, much more precise way to estimate it. Our equation is P of x equals 40.6x. What that means is that the probability that it will rain a number of inches at a particular place during a particular thunderstorm. Okay, so the probability that it rains 1 inch, how do we find the probability that it rains 1 inch? Plug in 1 for x, because we're asking for the probability. X is the number of inches. So can everybody do that for me? Plug in 1 for x. So what you get? Okay, so this is going to be 24, and when we're talking about probability, we're talking about percentage. We are units here, so there's a 24% chance, probability, that it's going to rain. By how much and in what direction so it's asking for a rate of change here, and if it's positive or negative. Is it going to decrease or is it going to increase? Does the probability change from x equals 1 to x equals 1.1? What's the average rate of change from 1 to 1.1, and make sure to include your units and discuss why the rate is negative. We're not getting to this part quite yet. Here we're just working what types of rates of change. Is it asking for instantaneous? No, it's asking for average. Okay, so we're going to set up our average rates of change here. So from 1 to 1.1, that's my span of time. And so when you find slope, it's the change in your y values divided by the change in your x values. Okay, so slope equals rate of change equals rise over run. That's what we're seeing up here. The reason I'm having you write this stuff down more than once in this note packet is because I want you to be very familiar with the fact that all three of these things all mean the same thing. So depending on what's given to you, you know you approach it the same way. So slope equals rate of change equals rise over run. We're going to look for change of P of x divided by change in your x. Now, change in y, but since our y values are given to us by this function, that's why I said P of x. The two values that we're looking for here are 1.1 and 1. Remember, it doesn't matter which one goes first as long as you're consistent. All right? So I'm going to put in 1 first. And when I put in 1, what did I get? We already did that part. I got 24. So P of 1 minus P of 1.1 all over 1 minus 1.1. P of 1 was 24. What is 1.1 if I plug in 1.1? 22.804. Okay, and 1 minus 1.1 gives me negative 0.1. And so what do you think we then do there? How do I get my average rate of change? Subtract and divide. All right, so let's go ahead and do that. What do we get? Negative 11 point what? 96. Okay, what are my units here? Yeah. Inches. Inches per probability per chance. So that's going to be a little tricky to write out, but those are our units. If we look at our units here on our axes, the graph of P of x is the probability. So we're going to use percentage to represent probability, so inch per chance. Okay, so by how much and in what direction does the probability change? That's how much the chance or the probability is going to change between x equals 1, x equals 1.1. So for B, we're going to now work with average rates of change to find the estimate of the instantaneous rate of change. Instead of doing this for 1.01 and then 1.001 and like kind of what we did before, we're going to streamline by actually writing our equation for r of x that's going to look very similar to this and putting the average rate of change function in and then using our table. Okay? So r of x, we're looking for the rate of change of p of x from 1 to x. So it's going to look very similar to this, except instead of plugging in a particular 1.1, we're just going to plug in what? Hold on. Up here, I wanted between 1 and 1.1, right? So I plugged in 1 and 1.1 into my rate of change equation here. Now I want between 1 and x, so I'm going to plug in 1 and x. Okay? So r of x, we have p of 1 minus p of x. It's the same setup. We're just changing it from particular x value that we're plugging in to just x in general, because then I can use my table to plug in whatever x's I want. And then on the bottom, I have 1 minus x again. Now, I know what p of 1 is. P of 1 is what? 24. But I can't easily plug in p of x into my calculator because that's what I'm looking for here. But do I know what p of x is equal to? No. What is p of x equal to? 40.6 x. So your p of x is just your function. And then on the bottom here we have 1 minus x. That is what we're going to put into my calculator. This represents your average rate of change at any x. And so maybe we need to label that for you. So average rate of change at any x is the same setup we used before up here. Just now we're plugging in x. And then in our calculator, we're going to actually put that in. So under y equals, you're going to put in 24 minus and then 40 times 0.6 to x. And I should have actually put parentheses over that whole numerator. And we're going to divide that by 1 minus x. Okay. And then we're not going to graph it. I've already been given a rough sketch of the graph. What I'm concerned about is trying a bunch of x's like I did before with the door example to get closer and closer and closer to hopefully the actual value. So I'm going to go to the table. I'm going to go ahead and clear all those out. And the x values that we want to try have to be really, really close to the x value that we're looking for. What is the x value that we're looking for? What's the x value we're looking for? 1. Okay. So we're going to plug in values that are really, really close to 1. So 1, I should get an error. Why do I get an error there? Because it's 0 on the bottom. Okay, so that's why we're going to have to estimate using this process, because we can't just plug in 1 for this average rate of change. Because if you plug in 1, what you're saying is what's happening at the instant, x is 1, but we can't divide by 0. So we're going to try 1.1. Does that match up with what I had before? Close? Okay. I'm going to try 1.01, make the span of time a little bit less. 1.001, 1.0001. Do I see something happening with the rates of change here?
They are decreasing.
They're decreasing, but are they starting to level out?
Yes.
Yes. Okay. So I'm going to go ahead and make a little table here. X and r of x. And I want to make sure you're very clear. This function that you've plugged in is the average rate of change. It's not your original function, which would just give you straight y values. These y values that you're writing here are rates of change values. So we plugged in 1.1, we plugged in 1.01, 1.001, and 1.0001. Okay, so you get negative 11.95, negative 12.23, 12.26, negative 12.26. These are all rate change values. Okay, so when looking at this table, as your span of time gets closer and closer and closer to being 0, meaning you're getting closer and closer and closer to it just being the instant of 1, because the time span between 1 and 1.0001 is 10,000ths of a second, so it's like very quick. What is the estimate then for our instantaneous rate of change at 1? Negative 12.26. Looks like it's bottoming out here, so I think it's a good estimate here. Our estimate of the derivative, remember, because derivative is instantaneous rate of change, is negative 12.26 inches per chance. So that's your estimate of your derivative in this case. Okay. Any questions here for this one? No? All right. We got one left here. All right. So estimate derivative using a table of values. Now this one you're not given any sort of function to work with. So we're going to set up a table of our own. You'd have to be given a table, and you can see from the example that I gave you table of values here. But up here, we're going to set up our own table to find the estimate of the derivative. And it's going to be average rate, change in y over change in x. And then the next spot will be average of your rates. Okay, I'll explain what that is once we actually bring the problem. But you set up your own kind of grid to work with the data that's given to you. And then for number 2, for the C value in question, meaning whatever time frame they want you to look at or estimate the speed at, you're going to find the average rates above and below. All right. And then we're going to average those average rates. Make sure to include units. It'll make more sense when we actually do this problem. What I mean by averaging the average. All right, so for example 3, we're looking at a mass bouncing up and down on a spring hanging from a ceiling. Its distance in feet from the ceiling is measured by a calculated distance probe every 1/10 of a second. So that kind of distance probe just gives you a data set. It doesn't give you an equation, it just gives you a table of values. So your time is seconds, and then this is the distance from the ceiling. So question here, when the weight is when the spring is almost extended, is your function increasing or decreasing? Well, not if it's at the very, very bottom, but if it's on its way down, so the spring is being extended or stretched, it would be increasing because your function is the distance from the ceiling, and your distance is increasing, right? And so as it's springing back up towards the ceiling, then your function would be shrinking, so decreasing. Okay, so now we understand what's going on here. So we're looking for how fast. Now, how fast is another way to say find the derivative. So how fast is y changing at the instant time is 0.3, 0.6, and 1. And I'm going to split this into 3 little sections here. We have 3 different time values. Now, at 0.3, we are looking to find an average rate, and we need to find 2 average rates, and we're going to use the values that are above and below. So the time value directly above 0.3 is 0.2. The value directly below 0.3 is 0.4. Okay. So in that first little chart here, average rate, you're going to find the change in x over the change in y over the change in x for these 2 values. So find the slope between those two values, if you will. And then we're going to find the slope between those two values. Alright, so change in y over change in x. For between 0.3 and 0.2, it doesn't matter what way you do it. If I use the 0.2 value first, it would be 3.99 minus 5.84, all divided by 0.2 minus 0.3. Okay, we're going to need some calculator work here. Go ahead and punch that out for me.
Josh, you got it.
Brennan?
18.5.
18.5? Somebody else get it?
That is correct.
Okay, so 18.5. And then another change in y over change in x, but this time I'm going to use the values on the other side of 0.3. So now 5.84 minus what? Yeah, 5.84 minus 7.37. You're still subtracting your y values, but now you're using two different y's and x's. So 0.3 and 0.4. What is this average rate of change? Brendan again, and then we'll double check. 15.3. Yep, okay. Now, that's a pretty large spread in terms of average rates of change. So this is where we find averages, and then what do we do with these two, do you think? We take the average of the averages, okay? So you take the average of the average rates. So average of the average rates. And I'm just labeling it for this first one so that you kind of see what we do there. So you find your average rates, and then we add up 18.5 and 15.3 and divide by what? 2. What do we get there? 16.9. Okay, when you have a data set like this is as precise as you can really get. So you find the averages using the values above and below, the average rates of change, and then you average the averages. Now we need some units here. What are units, Kenny?
Units would be the distance.
Right, which is in
Feet. Oh, feet.
feet, and then, yeah, over seconds. Good. So feet per second. We're going to do B together, and then I'm going to have you do C on your own, and make sure we can do it on our own here. So with 0.6, I'm going to use the value above and below. So I'm going to start with the 0.5. So my first average rate, change in y over change in x, is going to be 8 minus 7.48, all divided by 0.5 minus 0.6. All right? Yep. What do I get there? Negative 5.2. Somebody else confirm? So I was going to double check. All right, excellent. Okay, and then the next setup would be on the other side of 0.6, so we have to take 7.48 and subtract 6.01 and divide by 0.6 minus 0.7. What do we get there? Negative 14.7? All right. Now, again, those are pretty spread apart, so that's why we do this other step where we find the averages of the average rates. So, adding up, negative 5.2 plus negative 14.7 and dividing it by 2 gives me negative 9.95, and that's feet per second. Okay, and then I want you guys to do C, if you would. C on your own. Yeah, that one. So then you just do the first one. Yep. Yep. Use the data. You have to use the data that's given to you. Bree, would you tell me how you set it up?
2.63 minus 2.0 divided by 0.9 minus 1.
Good. Just a quick question. Could I have these values flipped?
Yeah.
If they're all flipped, yeah. Okay. And then when you calculate that out, what did you get? Kenny?
I got negative 6.3.
Is that what everybody else got? Okay. So negative 0.63, this would be feet per second.
I'm sorry.
Negative 6.3?
Yep.
Thank you. All right, so negative 6.3. I can't do another step in here, can I?
No.
No, because I don't have another value to work with. So that's going to happen sometimes. But if you have a value above and below, then the best average or the best estimate that you can do is when you take the average of the averages on either side. So for B, at t equals 0.3 seconds, is the mass going up or down?
No, it's going. Yeah, it's going up.
It's getting
Further away, but
It's getting further away, which means what direction is the mass going then?
Down.
down, so it's increasing.
It's going down. It's increasing. We know it's increasing because it's a positive rate. So we should probably say that. 0.9 feet per second. Positive. Meaning your distance is increasing. So if your distance is increasing, then the mass, since it's attached to the ceiling, would be going down. So it's on its way down. So the mass is going down. We'll just end it there. So the mass is going down. Okay. Any other questions on example 1, 2, or 3? Okay, so that's the three ways that your information will be given to you. Either be given a graph where you sketch in the tangent line and then estimate the slope by just counting boxes. You'll be given a function, which this is the only one we really calculate for by making rates equation, putting that in, and then using the table. So that's the one that might take a little bit more work than others. And then for example 3, we're just finding a bunch of slope values and then averaging. Okay. That's where we'll end today on this one. And if you would open up iTunes, you already downloaded today. Go to D1 practice that you had yesterday. Open, so we started it.